This is mini lecture number 4. We're going to cover a concept that's fairly fundamental and basic in electric circuit. It has some application in circuit solutions, so we're going to talk about what are the applications. It also be part of your first quiz, subject of your first quiz. It is current and voltage divisions. In essence, what current and voltage divisions are is two simple circuits that allow you to go from a particular voltage to drop down to a lesser value by using a series of resistors. That's voltage division. And in terms of current division, it allows you to go from a set current to a lesser current by using a parallel combination of resistors. You can select those values of those two resistors so that you can get the appropriate current in that resistor. Okay, so that's the basic concept here. In terms of circuit analysis, they actually represent a limited, and I say limited, I underscore limited method to analyze some basic circuits. And what are these basic circuits? Circuits that have one independent voltage source or one independent current source and resistors that can be combined either in series or in parallel. So for this limited kind of class, if you will, of circuits, voltage and current divisions are a possible solution for those. Of course, anytime we're talking about series combination of resistors or parallel combination of resistors, I want to basically raise a flag to remind you to make sure that you just don't have a visual and just conclude something is in series or in parallel. If you have two resistors in series, they must share the same current. And if you have two resistors in parallel, they must share the same voltage, which means essentially having both nodes in common. So just keep that in mind. So what we'll do at the end of this lecture, I'm going to put a problem for the first time and ask you to essentially either pause the video or stop the video, spend half hour solving the problem and come back to look at the solution, because we're going to do that in many of those mini lectures as a way for you to do kind of an in-class practice, if you will, even if it's virtual. Okay, so let's look at voltage division. Voltage division essentially states if you have a known voltage, in this case Vs, so this, you can look at this as connected to some other part of the circuit, but let's assume we know Vs, and Vs could also be a source, but we know the value of Vs. How much of that Vs is going to be found on two resistors in series, R1 and R2? Very easy to prove that. So these are the answers. Very easy to prove that. You can, if you realize that R1 and R2 are two resistors in series, so I can combine them by just simply adding their values and get an equivalent resistor. Once I do that, I can use Ohm's law to get the current I, which is Vs divided by R1 and R1 plus R2. And once I get the current I by Ohm's law, I can calculate V1. V1 essentially becomes R1 times I, and V2 becomes R2 times I. So simple construct, simple result, but allows you to go from a known voltage to a lesser voltage by essentially selecting the appropriate resistors to get the voltage you want across that resistor. That's called a voltage divider circuit. Limited values, but fundamental concept. Similarly, for current, we have a similar situation, except for current, it's a parallel combination. So in terms of current division, we have a known current, IS. We have some current that we know that's coming from somewhere else, could be coming from a source, could be also coming from a different part of the circuit, all right? And then we want to know how much of that current is going to be found in each of those two parallel resistors. And remember, I've been using the analogy for current, the water pipe analogy. It's like the water, essentially, you have a big pipe coming and it goes into two different size pipe, different cross sections, so different, if you will, resistance. So we want to know how much water comes into each side as compared to the water that's coming into the big pipe. So in order to prove this, we can actually put these two resistors in parallel. The parallel combination of R1 and R2 would be R1 times R2 divided by R1 plus R2. Once we get the equivalent resistance, then we can get the voltage V. V would be the equivalent resistance multiplied by RS. And once we have V, we can get I1 by taking V divided by R1, or we can get I2 by taking V divided by R2, because we recognize that the parallel combinations share the same voltage. Okay, so this is current divider. We're going to use this to solve some basic circuits for the remainder of this mini lecture. The next lecture is going to be an important, not that this one is not, but it's going to be what I call a signature lecture, because we're going to essentially begin describing nodal analysis for solving circuits with no voltage sources, and then general circuits. Okay, so let's look at an example how we might use this. The example should essentially also, you should keep in mind that not only your homework assignment has this sort of examples, these sort of problems, but your quiz will have problems like this. Your first quiz will be somewhat limited. So let's look at the first example we have. You have a circuit. Again, keep in mind voltage and current divisions are useful when you have one independent source, whether it's current or voltage type, and resistors that can be combined. So let's do a little bit of an analysis of the circuit that we have. We obviously have one voltage source, a 20-volt source, and we have some resistors. So can they be combined? Clearly, the 5 and the 1 are in series. Okay, that's pretty easy to see. The current that's on the 5 would be the current on the 1. There's no other place for the current to go. We can clearly see that the 2 ohm and the 4 ohm are also in series. So I2 that's coming down the 2 will find itself also on the 4 ohms. And the combination of I2, the combination of the 2 ohm and the 4 ohm, which would give us 6 ohm, will be in parallel with the 3 ohm. Okay, so this is a circuit that we, via series and parallel combinations, we can actually combine these resistors. Okay, and that's kind of a requirement if you're going to use voltage and current division. So it's a limited requirement. So let me tell you what I'm going to do a little bit just ahead. So by the way, one thing that I want to emphasize in this particular problem, you often can come up with a method of solution that's fairly, there are many ways that you can come up with these solutions. All right. So what I'm going to do in this, I'm going to try to use voltage division and current division so that we can have an example of both of those. Okay. So what I'm going to do here, I am going to combine all of those resistors in my blob here into one equivalent resistor. So I'm going to combine those into one equivalent resistor. And once I do that, I'll be ready and I'll apply voltage division to find the voltage V5. Okay. So once I get V5, then I'm going to find Ohm's law. I'm going to find, using Ohm's law, I'm going to find the current I. That's what this says, the current I. By essentially, the current I will be V5 divided by 5, just via Ohm's law. And once I know the current, then I can apply current division right here where I have the X. I can apply current division to get I2. So I need you to start thinking of the strategy when you get a problem so that you have some basis grounded, obviously, in science and good engineering technology, how to proceed to solving the problem. So that's what we're going to do here. All right. So the first thing that I do, which is the obvious steps, I can combine the 2 and the 4. They are in series on the rev, and that's going to give me 6 ohm. So you can now see a number of things here. You can see that the 3 and the 6 on my circuit on the right, they are in parallel. So I'm going to do 2 steps at once. Strongly recommend as you start these problems, you do 1 step at a time until you feel comfortable doing more than that. But just be aware that I'm advising you to do 1 step at a time. So what I'm going to do in my next step, I'm going to put the 6 and the 3 in parallel. And then I'm realize that the result is going to be in series with the 1 ohm. So I'm going to do 2 steps at once in my next step. Okay. So this is what this means, the 6 and the 3 in parallel with the 3 ohms. That's what this symbolizes here. The 6 ohm in parallel with the 3 ohm and then in series with the 1 ohm. So you get this. So the 6 in parallel with the 3 gives you 6 times 3 over 9. So it gives you 2 ohms. Okay. 18 divided by 9. And then when I add the 1 ohm in series, I get the 3 ohms. Okay, so this is a tailor-made circuit for voltage division. A voltage source in series with two resistors. So I can use voltage division to get V5, which is what I do here. And once I get V5, I can use Ohm's law to get the current I, V5 divided by 5. And the current I becomes 3 amps. So this is kind of a standard procedure as we use these methods. These methods are limited. They're not full methods. So you kind of have to, we usually combine resistors, and then we use voltage and current or current division to get some current or voltage across elements, and Ohm's law as well. So now that I have I, then I go back to the circuit, the original circuit. Of course, not quite the original because the 6 ohm is combined here. The original circuit had a 2 ohm and a 4 ohm, but I can use current division right here to go from I to I2. Now, remember, when we have current division, you need to know current division also has to do with the direction of the current. That is, the current is coming in here, and then it drops essentially here and here. Okay, so when we do current division, the direction of the current is important. So here, I2 is the current I, which is 3 amp, multiplied by the resistor 3 ohms, divided by the sum of the two resistors in parallel. So we get I2 being 1 amp. Simple problem, but it illustrates both current and voltage division, which is what we were hoping to do. Okay. I'm going to do one more, and then we're going to pause, and I'm going to put a problem for you to do, hoping that you pause the solution, get it, try to spend half hour, and then come back and look. Okay. Okay, so let's look at a second problem, which is a little bit more challenging questions. So here I'm asking you to find the power absorbed or generated. So whenever we talk about power absorbed or generated, in this particular case, in your mind, you should be thinking resistors never generate power. All resistors ever do is dissipate power. So we have one source. Again, we're dealing with one source circuits, limited circuits. So that source is going to generate power, and that power is going to be dissipated in all the resistors. So if our solution is correct, we should be able to look at the power from the source and make sure that it equals the power distributed by the 2 ohms, the 3 ohms, the 4 ohms, and so on, the sum of the power in the resistors. That's kind of a check for us. And mostly here, I'm going to be using current division. Okay. So the other thing that I want to say here, we're going to look at power formulations, essentially power formulas for the resistors. The most general power formula is voltage times current. For the resistor, you have to apply passive sign convention. So the power relates to the passive sign convention. For the source, the only power form we have is voltage times current. But voltage times current with essentially the voltage that I'm drawing here. The current must enter the negative terminal. Okay. So just know that. So we need to, if we have a current source and I ask you for power, you need to calculate the voltage. If you have a voltage source, you need to find the current, because for sources, the only formula we have for power is voltage times current. Okay. So couple of notes here. Let me just clean up, and then I'll go back here. So I'm looking at this circuit here. I can see what's in series, what's in parallel. I don't think that's too difficult to see that the 5 ohm and the 6 ohm are in series, right? So when I add them in series, they're going to give me 11 ohms, all right? I can also see that the 8 ohms and the 3 ohms are in parallel. And that combination of the 8 and 3 will be in series with the 4 ohms. Okay. So before I start combining, though, I need to put some current or voltage, or both, but mostly usually I put one or the other on these elements so that I keep track of where I am as I'm combining. So the next circuit here, I assign some voltage and current. Now, I try to follow the passive sign convention. You can see for my currents here, I try to assign for the resistors passive sign, my voltage V1 having a positive polarity on the left and a negative on the right, because the current 4 amp is coming into it. For the 5 ohm, you got the V2 here, but on purposely here, I'm assigning the V3. Oh, my 3 is not right, but I'm assigning the voltage on the 6 ohm as the minus on top, the plus. I'm doing it on purpose to show you, even when you don't have the passive sign convention enforced, you can still work the problem through. All right. So we try to essentially follow the passive sign convention when we label things in the circuit. So this is a circuit I'm going to combine. And as I combine the circuits, I'm going to lose pieces of it. Okay. So the first combination I'm going to do several things at once. I'm going to combine the 5 ohm and the 6 in series. That's going to give me 11 ohms. When I combine the 5 and the 6 ohm in series, I won't lose I1. I1 will still be there, but I'm going to be losing V2 and V3. So V2 and V3 will disappear when I combine them in series, but I1 will remain. The other thing I'm going to do, I'm going to combine that entire leg on the right here. I'm going to combine the 8 and the 3 in parallel, and then I'm going to add them in that the result of that in series to the 4 ohms. When I do this, the only thing that will remain is going to be I2. I'm going to lose V4. I'm going to lose I3. I'm going to lose I4, and I'm going to use V5. I'm going to lose V5. Okay. So here's the end result. Well, no, that's just one more. This is the end result of what I'm saying here. I've combined the 6 and the 5. That gave me the 11 ohm, and that's the right hand that I had, where the 8, essentially the 8 in parallel with the 3, and then in series with I think 4 ohms was the series combination. Okay. At this point here, you can see this is a textbook current division problem. You got a current source coming in, 4 ohm coming in, and right here, I can do current division to get I1 and I2, which is what I'm going to do. So I1 is 4 amps times 6.2 ohm divided by the sum of these resistors in parallel, 6.2 plus 11. I also, the same way, can get I2 and find I2 to be 2.56 amp. Okay, please note that KCL, Kirchhoff current law, applies. You can note that the 4 amp will be equal to I1 plus I2. Essentially, what you're looking at in current division is the current subdividing into the 2 parallel resistors that we have. Okay. Then I can go back to the original circuit, and now I have I2. So I can now apply current division here to get I3 and I4. So that's the way these problems, they're limited. It's a limited solution, but it allows you to solve some basic circuits. Okay. So if I do current division where I'm pointing out where I have the X here, I get I3 to be 0.7. I'm going to do current division in the same place and get I4 using current. Now, notice that I could have done, once I get I3, I could have done a KCL and get I4 because I2 is going to be equal to I3 plus I4. So that's also an option you have. But just to show you current division, to try to be more intentional about it, we do it again to get I4. Okay. So at this point, we have every current. I believe we got I1, I2, I3, and I4. So we can actually answer power question for the resistors. Remember, for the resistor, we have 3 alternative power formula. Voltage times current, which is the general power formula for everything. And then for the resistor in particular, we have resistance times current square. So we can actually calculate power for the resistors, because we could use essentially their current, square it, and multiply by the resistance. We also can, the third formula is voltage squared divided by resistance. Of course, we don't have. So I'm actually just going to calculate voltage here. And the reason I'm going to do that is because to show you, I want to show you V3. I want to show you V3, even though I don't follow the passive sign convention. V3 is entering, the current I1 is entering the negative terminal. We can still calculate the voltage. So we'll do that. Aside also, I need the voltage V, which I have here, across the 4 amp. And there is no Ohm's law for sources. So one way to calculate the voltage V across the 4 amp with the polarities that I have, so that the current on the source is entering the negative terminal, I'm going to do a KVL, Kirchhoff voltage law, in that loop here. Okay, when I do that in that loop, that's going to give me V if I know V1, V2, and V3. So let's go out here, let's calculate. I know the current. Let's calculate the individual voltage for all the resistors. Voltage, resistance times current. Ohm's law. So I find V1, I find V2, Here you can see V3. V3, essentially, I have to put a minus sign because the current is entering the negative terminal of the voltage. So that's how you handle not satisfying the passive sign convention in terms of Ohm's law. Okay, that's V3. And then I go on and calculate V4, V5. And then, as I said, we do a KVL in this loop to get the voltage V, which is the voltage across the 4 amp. I'll need that for power. We do that by using the voltage V1, V2, and V3 and get 23.86 volts. Now I'm ready to calculate power. So I'm actually going to calculate power using V times I, even for the resistors. The voltage times current is the most general power calculation, so I can do that. So I go ahead, and all I have to worry when I do this, that the passive sign convention is satisfied. So it is for the 2 ohms, the voltage and the current enters the right way, current entered the positive, also for the 5 ohms, but it is not for the 6 ohm. The current is entering the negative, so I have to put a minus sign. Okay. So note that you can never find a negative power for a resistor. So just so you know that this is just not something that you can never do. All right. So we finished that to get the other resistors. Nothing special here. And then, of course, we have to calculate the power for the 4 amp source, which is the for the 4 amp, which is 4 amps, not 4 volt, 4 amps multiplied by 23.86 volt. So it should be 4 amp in that equation. So that should be 4 amp. And we get 95.44 watts. And if we did things correctly, it should equal to the sum of the power that the resistors dissipate. Power produced should be power dissipated. Okay. So that's in essence the 2 examples. We started with somewhat of a small examples. This is a little bit more complex. You should expect something like that in quiz number 1. So what I'm going to do right now, I'm going to pause. I'm going to bring in a problem for you to work on. And I'm going to ask that you either pause the video or stop the video and give yourself half an hour to do it. Okay. And then come back and look at the solutions. So this is a problem for you. Okay. That I expect you to be in a position right now to do some work to at least move a little bit, even if you don't get it totally right, to be able to move into this. So I'm hoping that at this point, you get this problem on paper. You then stop the video or pause it, go work for half hour, and then come back. So again, this is the kind of problems we can solve with current and voltage division. One source, one independent source, in this case, a current source. All right, and resistors that can be combined. So if I look at the resistors here, I can clearly see that the 1 ohm and the 7 ohm are in series. I can see that the 4 and the 5 are in parallel. I can see that the 3 and the 6 are in series, and the result is in series with the combination, the parallel combination of the 4 and 5. So things are nicely in series and in parallel. And the question you're being asked is to calculate the power either generated or produced, either absorbed or produced by each element. You should be able to think automatically. The resistors are going to dissipate, are going to absorb power, and the source here is going to produce power. The sum of the power should be the same, should be equal. Power produced should be equal power dissipated. Okay. All right. So I'm going to do a few things all at once again, because I'm hoping you're getting a little bit the hang of it here. The first thing I'm going to do, I'm going to combine that entire leg here on the right into an equivalent resistance. I first combine the 4 and the 5 in parallel. That gives me 4 times 5 over 4 plus 5. So that gives me 20 over 9. And then I add that to the 3 ohm and to the 6 ohm because that result will be in series with both the 3 and the 6. The end result here is 11.2. Don't expect nice round numbers from me. I don't worry about that. So don't expect that in quizzes and in computer-based exercise as well, or for that matter, exam. The second thing I do, I combine these two in series. They're fairly obvious that they're in series. Okay. So once I do that, so this is the end result here. So at this point, there are many choices I could have done to solve this problem. I'm going to actually go and solve it in a kind of more laborious way. There are more efficient way to solve this. So let me tell you how efficient, how one efficient way that I could have solved this. And then I'm going to go back and do it a different way. Okay. I actually could combine, I should be able to realize that all of the elements here are in parallel. They share both nodes. They share this node, all of them share that node, and all of them share that node. So everything is in parallel. So I have one current source, and then I have 3 resistors in parallel. Okay. So one of the things I could do, actually, I could have just combined all of the resistors in parallel, the 3 resistors, and find the voltage VA. Okay. I could have combined the 8 ohm, the 2 ohm, and the 11.2 in parallel, and then calculate the equivalent resistor from these 3 resistors. Once I find that equivalent resistor, I could find VA by multiplying the equivalent resistance multiplied by 1 amp to give me VA. Once I have VA, I can take VA. I can find I1 VA divided by 8. I can find I2 VA divided by 2, and I can find I3 VA divided by 11.2. So that's kind of a nice, efficient way to do it. I'm not going to do that here so that I can, again, overemphasize current division for you. What I'm going to do instead, I'm going to combine two of the resistors and leave one, and then find that current. So you're going to see what I'm doing here. So here, the first thing I do, I combine the 8 ohm and the 11.2 ohm. Okay. I combine the 8 and the 11.2, and that gets me 467 ohm. And then I find I2 from current division. So, okay. So then I can calculate I2 by straight application of current division to find I2 to be 0.7. Then I go back and I'm going to now combine the 2 ohm and the 11.2 and then find I1. So I'm combining 2 of the resistors and find the other current. Because when you combine the 2 resistors, you lose those 2 currents. Okay, so I'm finding the other current so I'm doing this 3 times. Kind of redundant, kind of laborious, but it makes the point, which is what I'm trying to do here, and I find I1. Finally, I combine the 2 ohm and the 8 ohm to get 1.6, and I find I3. Okay. So use over and over current division by combining different resistors. Now that I have I3, I2, and I1, I can use current division here to get I4 and I5 at the X point, because I3 is coming into a parallel combination of the 4 and the 5. So I get I4, and I can do that again and get I5, or I could have done KCL here and get I5 from I3 and I4. Okay. So now I actually have all of the currents here. All right. All of the currents. So I can use this one of the power formula for the resistor because I have current. So I can use R times I squared. And I can calculate for each resistor the power that resistor dissipates since I know the current. For the example, for 1 ohm, I get 0.03 watts. So I can do that for every resistor in the circuit. Okay. For the 3, for the 4, nothing specific about those, just straight calculation from current. For the current source, though, I need the voltage here with this polarity. I need that voltage. Let's call it Vs. I need that voltage so that the current enters the negative terminal. So the power for the 1 amp is 1 amp times Vs. But what is Vs? Vs is also the voltage. You have to recognize that the current source is in parallel with the 2 ohm. So Vs is also the voltage across the 2 ohm. So I can calculate that by simply 2 ohms times I2. So I get 1.4 watts being generated by current source. And then just to verify that the power that the 1 amp puts out should be equal to the power dissipated by all the resistors and when you sum them up. Okay. So that's an example I'm hoping you did spend a half hour and do. So let me do a little wrap up and a little look ahead. So where are we right now? Okay, where are we right now? By way of recap, we've essentially started by defining current, voltage, power. We also introduced sources. We talk about independent sources, dependent sources. Then we introduce resistors, okay? And mainly when we introduce passive elements, we look at the voltage-current relationship. For resistor, it's called Ohm's law. So we introduce Ohm's law. We talk about the dependence of Ohm's law on the sign convention, the passive sign convention. Then we introduce nodes and loops. What is a node? What is a loop? And we need those to do Kirchhoff current law and Kirchhoff voltage law. Okay, so we don't have to do Kirchhoff current law, Kirchhoff voltage law. These are pieces that we're going to basically put together in the next lecture into a full method. So we also learn how to combine resistors in series and in parallel. We spend some time making sure that you're not combining resistors that are not, you're not imagining being in series or in parallel. We talk about power calculation and its dependence on the sign convention. And of course, we finished this entire segment today by current and voltage division, that they are limited method of solution for basic circuit with one source and resistors that can be combined. So the next lecture is going to be a signature lecture. We're going to be looking at developing nodal analysis for circuits with no voltage sources. That's going to be a class of circuits. The next significant lecture would be general circuit that have anything. So these are important things to look for.